I'm going to talk a bit more in detail about wavelet derivation and a specific tool that we have here at VHP to help out with that wavelet derivation. And it becomes quite handy when you're trying to normalize out your AEO, okay? And to convert from these millivolts of near far stacks into something that can be compared to near and far reflection coefficients as they get modeled. And let's first of all sort of talk about really what we really try to do. And we start off with one of these well reflectivities, okay, which ends up being a derivative of log rho v. And we then need to go and take this well log, which you notice is in depth, okay, and we're going to want to compare it to a seismic, which is in time, okay? I think somebody right now says, oh, I have depth migration. It's already in depth. Everything's done, so I don't need to worry about these time to depth correlations. No, okay? The difference is that now you're worried about a depth to depth mapping, okay? So instead of having units of velocity for the transformation, you just have dimensionless units, which is a migrated depth to true depth, okay? And so that, again, this particular thing is not, sort of solved if you have things in depth. And also, I think a lot of people will go and say, okay, we go and take these very careful depth migrations, and we say, okay, if we're going to go and do a wavelet derivation, could you please take your depth model and stretch it back to time for us? You say, well, it's already in depth. Why don't you just work with it in depth, okay? Well, there are sort of two major problems with that. That first is that there is a lot of differential stretch as you come down in the record if you're at depth. In other words, that the wavelet changes very quickly. Also, if you take a look closely at the theory behind wavelet derivation, there is inherent in it a Born approximation, which is patently violated if you try to do one of these wavelet derivations in depth, okay? So you will see us go and say, if we're going to do a wavelet derivation, if we're going to go and do a sparse spike inversion, if we're going to go and do a model-based inversion, we do have a strong preference to do that in time. For those of you coming from a seismic processing background, I don't think this is really a surprising statement, because what we're really doing here is wavelet processing. And within seismic processing streams, you really do your wavelet processing in time, for the very reasons that we prefer, or actually have strong preferences, to do our wavelet processing in time, albeit post-stack, okay? Now you've heard me, okay, that being said, that we need to go and have a time to depth mapping to take well log into seismic, okay? One way of getting a estimate of what's happening is with a VSP or check shot. And that's literally going and sort of shaking at different places in the hole and sort of listening, for, when you hear it at the other end, or vice versa, that you can go and have things on the surface and listen for them at different depths in the hole, okay? And you can therefore map between what would be the time for the seismic wave to move up versus you do know exactly where you were in the hole when you ended up having that, okay? And so, but there is some uncertainty about each of these. So you have a time to depth mapping with some uncertainties on it, okay? Now it gets a little bit more complicated than that, because a lot of times you'll go and have very good seismic reflectors, okay? And it actually, you will be a bit surprised, but many times a good seismic reflector, you can isolate it and know where it comes in to within a tenth or about 2/10 of a millisecond, okay? And if you have two seismic reflectors that you can know where they're coming in to within about 2/10 of a millisecond, that you actually can tell something about in more detail about the time to depth mapping. So many times we'll nominate other points associated with major seismic reflectors in order to go and have them particularly placed at the correct time. And so we have this check shot, we have some uncertainty on it, and one thing that we're going to want to therefore estimate is what should this check shot be in order to sort of optimize the overall process of the wavelet estimation, okay? So that's one thing that happens, okay? The other thing is, what is the wavelet, okay? And we go and have certain spline points, which are kind of the minimum number needed to satisfy the wavelet. And that's another particular thing that we're going to go and try to estimate. And in fact, we also estimate how long the wavelet should be, okay, is another thing that we go and say, is a short wavelet good enough, or is a long wavelet better? I mean, do we match better by sort of increasing it, or is it just what you'd expect by adding extra parameters to the fit, okay? Another thing that you end up having to worry about is exactly where is your well. Well, it isn't where is your well, it's where is your seismic. You know where your well is. Many times you're not quite sure where your seismic is, and I would go and have a little ex parte communication with Mark or Guy Duncan as to why this happens imaging wise. But you know, these particular events aren't always placed at the correct position in a left to right sense. And so there is some uncertainty in where you should be placing the seismic cubes. And then finally, you'd like to go and understand what is the noise level, or the amount of sort of mismatch between the synthetic that comes from convolving this well log after it's been converted to depth with this function with this wavelet from the synthetic versus the true seismic. Okay? Because I think when we all went through what would have been yesterday or early today, late yesterday or early today, the rock physics, you know, the question people have, why are you just putting this noise level at a third? Okay? Well, that actually occurred to me fairly early on too. What is the noise level in real units? And this starts providing you with what that noise level is in a quantitative way, and not just a back of the envelope sort of guesstimate of what the noise level should be. And so what's a particular wish list? We get what the wavelet is with uncertainty. We get the wavelet length. We get how much noise level's on there. We get these time to depth adjustments. We end up getting these positioning adjustments. We want to do this for multiple wells at once with multiple stacks and be able to handle deviated wells. Okay, the particular wavelet derivation we have fulfills this sort of practical wish list. I talked about estimating wavelet parameters, the check shot parameters. We have this registration problem. And lo and behold, we also go and estimate one other thing that's needed, which is B, okay? Is something else that can be estimated. And remember that in order to normalize our AVO, okay, that we observe to be equivalent to the model, we need to have the size of the near wavelet, the size of the far wavelet, and B, okay? And all three of those come out of this process, and the approximation that we make in the wavelet derivation is the same that is utilized in our forward modeling in the rock physics spreadsheet, and also is the same as the forward model that's used in delivery, as we will discuss tomorrow. And how do you go and do an AVO analysis? Well, you go and you get trends, you get your VP versus depth. Since this was in the same field and underneath sort of the same, on the same particular sort of pressure line, you can just go and have a simple depth relationship, and it works quite well. There is a very good VP-VS relationship here at Starlifter. Also a fairly good VP density or VP porosity relationships. And we go and we end up sort of forming the synthetics sort of before and I mean the synthetics of that well log so that we can sort of match to what happens. And a lot of people look at this and they say, what in the heck is a negative angle? Okay? Any idea about what a negative angle is here? Angle, it's angle of incidence.
Oh.
Okay?
Just
Well, if you go back to yesterday and sort of think of these rotated stacks, this goes from near to far, right? Okay, what do you think this goes to as you go from here to here? This actually goes from near to the gradient stack. And it's actually, you can go and talk about what the negative angles are, and that has an implication and sort of allows you to sort of go around the circle and see what these different rotated stacks will look like as you go around. And when you go and see that, that's actually sort of these synthetic rotated stacks. You can also go and understand what the placement uncertainty is. And as it turned out that we realized, if you looked at the seismic, that this point here corresponded to this point with about this much uncertainty in a sort of an up and down sense in terms of the way that this particular well was positioned, okay? And you sort of will go and say, well, can this be a value? I really don't think so. I mean, it's just exactly where this ties. Well, it ended up being important because as it turned out that that most of the pay, I think, ended up, if I remember rightly, ended up being in this sort of package. But the people who wrote the contracts had a different equity split depending upon what seismic loop it actually correlated to. And so it ended up going, in this case, whether or not this correlated to this or this correlated to that, ended up being fairly important. And to say that this correlated to this with this type of uncertainty ended up having equity implications in terms of this field. So it can actually sort of have direct sort of benefit. We also do that for the FAR. You can see here the uncertainty in the wavelet because we get a lot of different possible wavelets. Another thing that you notice is the wavelet's not very big, okay? I don't know if you're sort of used to seeing things in terms of derived wavelets, but they normally have a lot of little extra side lobes here on the end. And really those side lobes are just memorizing your seismic data. And it also slows down all of your synthetics. And so it turns out that you're much better off in most cases with a much shorter wavelet. And I haven't seen a case where the wavelet's longer than the main peak and the two side lobes. I mean, and we do that by sort of a student's t-test of adding extra parameters. And does it help out more than what you just expect by just adding another parameter to the fit? You end up getting the synthetics versus the actuals with a particular noise level being estimated, and that can go directly into your modeling. So we're not guesstimating how large it is anymore. And now this is the kind of I think the real interesting part for me, is that here are the extracted amplitudes that ended up coming out of the seismic data. And after we had this well and did the wavelet derivation, we found that the size of the near wavelet was about 1900. The far wavelet was 1600. We also had uncertainties about these, by the way. And also the size of the B coefficient was about 2. But now, knowing all three of these numbers from the wavelet derivation, we know that through the 2x2 matrix that we'll go and transform our observed amplitudes into reflection coefficients. And when you go and apply this matrix to this two-dimensional space, this gets transformed into this, okay? And notice there are some odd things happen. This thing gets rotated up so it actually even goes into a different quadrant. They also tend to end up being sort of squished down a bit. okay? And then as it turns out, if you compare this to the measured, you see that the particular down dip area sits in sort of one corner of the sort of the modeled possible brine responses, and the hydrocarbon is reasonably consistent with the overall ellipse associated with the average hydrocarbon response, okay? And as we go through, and I'll walk you through a couple of different methods of trying to understand what these particular factors are, okay, in exercise 7. And it's fairly close to what we did in practice, okay? Because before we went and had the well, we had to guess what these would be, okay? And we ended up having to do that by sort of knowing what, and you'll sort of see in the spreadsheet, how we sort of walk through and try to make sure that overall sort of things are consistent in terms of the prediction of, let's say, where the brine comes in, and then ask, is that if we go and align the brine so it's where it should be, where does the hydrocarbon in a relative AVO sense sit with respect to the brine once we've gone and aligned it properly, okay? It's not an easy thing. I think it's best learned by going through and asking yourself these questions. And this exercise walks you through it sort of step by step. But it turns out in South Africa, it's also a very significant AVO response. And so you're going to get some further practice in trying to determine what these normalization factors are. But then after you go and have a well, you can't have explicitly know what these numbers are in order to be able to sort of match up, okay? And it really is surprising the amount of ways these things can end up getting distorted in this space. And you'll go and you'll sort of ask, well, Mike, shouldn't you aspire to sort of more than this, that we'd expect a little bit better correspondence. You shouldn't be having to rotate stuff around and move it and stretch it and squeeze it with this 2x2 linear transformation. But I mean, it's one thing, I guess it's sort of an open challenge to sort of AVO analysis that is trying to get, sort of this direct correspondence. But you end up having a lot of things in processing. You have things such as anisotropy, you have interbed multiples, you have different types of radon deconvolution and other processes in the processing which really don't respect perfectly the amplitude versus offset behavior. And when you fold these together, it is the very, very rare occurrence that your modeled AVO response is reasonably close to the actual AVO response. And so what you really need to look for and be concerned about, and in terms of a good indication, is a difference in the AVO response. In other words, between your up dip and down dip. Let's say up dip brightens, down dip does not. Up dip dims, down dip brightens. A difference in the AVO response, and then to note that if I go and pin the AVO response of one of these things to be the correct behavior, is the other AVO response what I would expect, or the delta AVO response what I would expect. And a lot of this has to do with what Dave talked about when he went and looked at Gossman and what happens when you do fluid substitution. Because there is a very well-defined direction that things will move when you do a Gossman substitution. And that well-defined direction goes and says what the relative change should be between the two hydrocarbon legs. And that's the type of thing that we're looking for. It's relative AVO. It's not an absolute AVO unless you can go in and are good enough to have a well log. You always will have to go take a look at one of your reflectors, fix the AVO to be correct for that reflector, and ask whether or not other things are consistent and have the right relative AVO change. Okay? Now, I talked about that. Things in terms of the Bayesian update are very similar. Instead of having a one-dimensional conditional prior probability. You just have a multi-dimensional conditional prior probability. And all of the other particular formulas go through as you would expect. You can get those probabilities. You can integrate net sand. This is integrated over a lithology volume, and I'll talk to you a little bit about that in terms of the spreadsheet and where that comes from. But anyways, let's sort of go about what's important here. And a lot of things you're going to learn, the practical way. But AVO always needs a significant calibration to match the model response from the petrophysical information. The best way to do this is with a wavelet derivation. And for several reasons that we've talked about, that this wavelet derivation program that was developed for us by CSIRO in Melbourne, we really have found has been the preferred method of use, and is what we use on a daily basis. We use on a regular basis now. Okay. Any questions about this stuff? I know yesterday there were a lot of very blank stares at the end of my AVO lecture, and maybe tired or the like, but I also talked to some people afterwards. I think there was a particular level of confusion. Does that persist, or?
You said there was a spline fit on the wavelet?
Yes.
Do you use that splined wavelet to do your inversion on your data?
No, we actually...
Or do you actually use the raw numbers on its...
Well, internally, we end up using the spline points, or what we estimate. But in terms of what we output is on whatever digitization level that you want, and so it's actually a regularly sampled, say, 4 mil wavelet that's used for the inversion. Or whatever, if you want 2 mil, you just ask for it at 2 mil. But the thing is, though, that you have to be careful not to be estimating a lot of parameters that are linearly dependent. And so it's a detail that you have to be very careful about when you're doing this type of estimates.
Just a point of the slide is when we're doing the actual wavelet derivation and processing in seismic, we normally we go back to 1 millisecond to draw the wavelet, apply the operation to correct the wavelet, and then go back to 2 or 4 milliseconds and we're processing it. But whenever we do the actual wavelet processing, there's a curve such that.
Yeah, we would go and do a particular, in this case, do a spline interpolation back to the 1 mil. You don't want to be doing a lot of spline interpolations on the fly because they're fairly expensive. Okay,